Hello everyone, welcome to my video. My name is Ganjai, and in this video I'm going to explain about my project for subject BMID 2504. In this project, the product I selected for my team is metal turning lathe machine. So first of all is the product brief. So a metal turning lathe is actually a fundamental of manufacturing machine designed for perform operations such as rotating a workpiece against a stationary cutting tools to form a final product. So in this project focusings are on the reverse engineering, geometric design and parametric 3D CAD modeling of a conventional industrial lathe machine. The major structure component includes the lathe bed, headstock, tailstock and also the carriage assembly. So next is our project planning. Our project durations was in within 7 weeks. We start on week 7. So in week 7 to 8, we have planning for machine selections and also preliminary two-hand sketches. For week 9 to week 10, we planning for machine component measurement and part modeling CAD. And to the third phase, week 12 to week 13, we're planning for sub-assembly, constraint, and FEA simulation setup. And finally is the week 14. After all those parts are done, we planning for realistic rendering and final documentation. And next is measurement technique. In this section, we're using two measurement tools, which is digital vernier calipers and also a measuring tape. So to guarantee precise accuracy during the model transition, digital vernier calipers are applied primarily for external and inner diameter, depth, and also thickness. For measuring tape, primarily used for capturing macro dimensions, primarily used for the expensive bedways and large carrier base. And next is some example of our initial product sketches for lathe machine. The parts including a hand wheel, tailstock, tool post, and slide and also compound rest. The purpose of the sketching was enable us more understanding about lead machine parts, geometry, and design to help us easy to create or drawing CAD file in future. After the hand sketch and measuring section was done, we transfer those measurement data and also sketching into a 3D CAD modeling using SolidWorks. And these are the examples of our 3D CAD modeling part, including compound rest slide and hand wheel, tool post, tailstock, carriage, and also chuck. Next, after the all CAD part was done create, we've chosen some essential part for finite element analysis. And the first part was chuck jaw, and its material was carbon steel, and its material yield strength is 350 to 500 megapascal. So for the result for chuck jaw, maximum bond missile stress of 12.77 megapascal is concentrated at the upper contact area. The stress remains well below typical material yield strength, ensuring its structural safety under clamping force. So for the maximum displacement of the chuck jaw is only 0.0515 mm, occurs at the upper corner of the jaw, which is hardly uh, indicates by raw eyes. The relative small displacement indicates that the chuck jaw maintains sufficient rigidity and it is unlikely to affect workpiece position accuracy during turning operations. Next, second part was the 2-bit. The material of the 2 bits is high-speed steel with yield strength of 1500 to 2500 megapascal. On this part, we apply two types of force, which is from y direction and also x direction, to simulate a situation that the 2-bit feeding to the material to cut the material. So the maximum displacement of the 2-bit occurs on y direction, which is 0.033 millimeters, confirming its standard bending response. And for the maximum stress occurs on the x-axis, which is 40.77 megapascal near to the fixed support, identifying this axis as a most critical loading direction. And then for comparing the result for maximum stress of 40.77 megapascal to the material yield strength of 1500 to 2500 megapascal, which proving this 2-bit material are sufficient for the normal turning operations without breaking. And the third selected component was the tailstock center. The material was also a high-speed steel with yield strength 1500 to 2500 megapascal. And the maximum stress for tailstock was 0.105 megapascal, and it occurs on the container tip, which contact with the workpiece creates a expected stress concentration. The cylindrical strength experience lower stress about 0.05 megapascal. Overall, the stress level are significantly lower than the material yield strength, which proving the parts was safe and sufficient for the turning operations. And next is the assembly. We assemble all the components and part into its design place and return it into a drawing which come with dimensions. And we also turn assembly into a exploded assembly and come with a bomb build of material. And our parts in total are 14 parts. First is bed and body, second tailstock, third shaft holder, apron, big slider, compound rest, slide bottom, compound rest, slide top, tools holder, shaft, chuck jaw, handwheel, adjuster, and last tailstock center. And after the part are done drawing and assembly, we turn the CAD file into a realistic rendering. The photorealistic rendering bridges the gap between digital modeling and physical reality. The final CAD assembly is visualized within a simulated factory environment. This process highlights surface finish, material selection like cast iron and chrome, and spatial relationship in an industrial context. And last but not least, the design improvement for the lead machine. So the first is mass optimization, reduce overall weight by optimizing non-critical structure areas without compromising rigidity. Second is operator safety, implement protective guards on rotating parts and moving components to meet strict industrial safety standards. And the third is ergonomic refinements, redesign handwheel and control lever to provide better grip and reduce operator fatigue during extended use. And last is maintenance accessibility, improve access to lubrication point and internal components to facilitate easier preventive maintenance.